Okay, so this is part three of our derivation of the D4h character table. And so far the last two videos, we're able to get the total number of symmetry operations, figure out that this is a 10 by 10 matrix with 10 irreducible representations that we're looking for. And we figured out three of them thus far. And so at this point, it's always good to look at to see if you can multiply different functions together to get new functions. And the one that we're going to do quite easily is we're going to multiply z and x times y. Now, the reason why we can do this is because we'll get a new function that is going to be an irreducible function. If we multiply something by gamma 1, for example, that's ones across the board. So anything times by gamma 1 is just going to get itself back. But if we multiply gamma 2 by gamma 9, what we get then is z times xy. And so we're going to get x, z, y, z. And those are going to transform together because x, y transform together. And so, and all we do here to figure this out very quickly, we could, think about how these transform, but much easier is we just say, hey, 1 times 2 is 2, 1 times 0 is 0, 1 times negative 2 is negative 2, negative 1 times 0 is 0, negative 1 times 0 is 0, negative 1 times negative 2 is 2, so we got to change there, 0, negative 1 times 1, and negative 1 times 2 is negative 2, and then 1 times 0 is 0, 1 times 0 is 0. So that got us very quickly the other irreducible representation that was two-dimensional. So that's going to save us a lot of time. And from here, we have to start thinking about other functions. We could go to the other quadratic functions. We're going to do that shortly. Let's do RZ. That's a rotation function, which is always a good one to check, especially for character tables where you have a lot of different irreducible representations that you have to derive. And so to remind you what the RZ function is, that is a rotation vector defined as wrapping across the z-axis. So there's the z-axis, which remember is coincident to our principal rotation axis. We have x, y, and z. And so if we have a change in the direction of rotation of this rotation vector, then that's going to go into negative itself. Of course, if we do an identity operation, that's the first class that we have to evaluate, we're going to get RZ just going to itself. So RZ goes to RZ. So we're going to get a 1 by 1 matrix equal 1. So that's 1. We're hoping we get some different value here that's not equal to gamma 1 or gamma 2 or gamma 9 or gamma 10, I guess, for that matter. Next, we're going to do a C4. And for the C4, we are going to think about how that changes RZ. Well, we have this RZ. And now we rotated it 90 degrees along the z. So we're spinning, this rotation vector is already spinning in one direction. We're just spinning it more in that same direction. So, maybe if we call this the tail and this the head, the tail is going to move 90 degrees and the head move 90 degrees, but we're still spinning in the same direction. So RZ goes to RZ, and so the value is 1 here. A C2, it's the same idea, except now we're doing 180-degree rotation across the z-axis. So again, RZ is just going to go to RZ. So we'll get a value of 1. But the C2 prime is going to be different here. So let's look about that. C2 prime, that's our next one. We are now, remember, C2 prime was a flip, a 180-degree flip along the x-axis, one of those C2 primes. That's how we defined it. And so we are flipping and kind of bisecting this, right? So if we think about, I'm going to draw it with the same perspective as it was to begin with, okay? And now we bisected it and it's flipped this way with the head and tail interconverted. So we're going one direction, or we're going, and the way I drew this here would be what, counterclockwise, and now we're going clockwise. So RZ goes to negative RZ. We'd have a 1 by one matrix with an element of negative 1 there, right? So we would have something like this. We wanted to be rigorous about this. And then we take the trace of this matrix, which is just a sum across the diagonals, of course. So the character the C2 prime operation would be equals to -1. So up here we do a -1. If we think about the C2 double prime, it's actually going to be very similar. It's going to do the same thing. And now instead of doing a rotation along the x, remember we're doing a rotation that way, but we're still going to be bisecting this rotation vector. And so it's going to flip. So you have a -1. Okay, what about the inversion operation? Inversion operation, a little bit tricky. Remember the definition of inversion is that x, y, z, any arbitrary point goes to -x, -y, -z. And so we have to think about how if we have some rotation vector, how is that going to transform with identity? And so what I like to do is think about 3 points here. I'll think about the tail, I'll think about the head, and then I'll think about the middle, maybe right there, and think about, to visualize this, how these points would transform. Remember, in words, what this x, y, z goes to -x, -y, -z means is that something at the top goes to the bottom, something in the back goes to the front, something in the left goes to the right. So let's use that to try to help us, right? We're going to the opposite. So this red point was at sort of the top of our drawing. So that means it's going to have to go to the bottom of our drawing. And then we have this green point here. This green point was on the left of our drawing. Now it's going to have to go to the right of our drawing. And then the tail was at the bottom of our drawing. And so now it's going to have to go to the top of our drawing, right? And we know we go red to green to the head, I guess. Red to green to the head, red to green to the head. So we're going to look like this. 3 points to define this curve. And look, we're rotating this way, counterclockwise, and we're still rotating clockwise. So that means RZ with inversion didn't do anything, still goes to the same direction. RZ goes to RZ. We have a value of 1 for the identity. What about S4? S4, remember, is a C4 followed by sigma H. Well, C4 we determined did nothing, and a sigma H is just a mirror plane in the XY plane, right? Well, this is above the XY plane, but if it looks at itself below the XY plane, it's still going to be going in the same direction. So sigma H does nothing. C4 previously determined did nothing. So they both do nothing. So RZ goes to RZ, and so we get a value of 1 there. And you can see we're in the midst of deriving something new. We don't have any function previously, any irreducible representation or vectors, what you could call, that transforms like this. Okay. What about sigma H? Well, we just went over sigma H, right? Sigma H did nothing as well. RZ went to RZ. So that is going to give us a value of 1. And then we have lastly sigma V and sigma D. And both the sigma D, V and sigma D are similar by the fact that they're going to be bisecting this rotation vector. So there was one of our sigma V's. We can see the head and tail are going to swap. They're looking at each other in the mirror. And same thing with our sigma D, they're going to swap. So they're changing directions. When they change directions, we get -1s. So that's how, fairly quickly, we're able to use the RZ function to derive something, and derive another reducible representation. All right, so now we've done RZ, we've done Z. It's time to explore the other quadratics. Remember, the quadratics are transformed as the d orbital functions. So there's 5 d orbitals. We have 2 of these that we derive, xz and yz. Those are 2 of the 5 d orbital functions. But we could look at some other ones, and we could look at z squared. That's another function, the orbital function. Problem is z squared is just z times z. And so when we times z by itself, we're just going to get gamma 1, right? Because all these 1s are going to become 1. when we square them, and all these negative ones are going to become ones when we square the negative ones. So we're just going to get ones, positive ones all across the board. That's just going to get us back gamma 1, so that doesn't help us. But we can do the other functions. And the other functions are, well, one of them is xy. And there's also x squared minus y squared. It doesn't really matter which one we do first. How about we do xy? And so we have to go back and think about how x and y transform. Well, we've already done this previously in the previous part 2 of this series when we were deriving how x comma y. This is different, right? This is two-dimensional. Looking at x and y individually, those happen to transform together. Now this is the product. It's a quadratic function. These were linear. This is x times y. But we can use the results from these, so I'll blast through it pretty quickly, where we saw that x went to x with identity, of course, x went to y, so therefore x times y just goes to x times y. So we're going to get a value of 1. Not very interesting. What about C2? Well, previously we found that x went to minus x. Again, see the previous video for where I'm getting this from. I'm just getting it from when we derived gamma 9. But it's a spinning 180-degree rotation, so x went to the negative self, y went to the negative self. But what's interesting here is now xy goes to what? Negative x times negative y, which equals xy. So xy went to xy. That's going to give us a positive 1. C2 prime. That one, our C2 prime, was defined as going along our x-axis here. And so this is x, y, and z. So if you have an x vector, that's not going to do anything. So x went to x. If you have, sorry, this was C2, guys. So I did C2. That is going to be 1. But we did not do C4. Anyway, we gotta do that in a sec. Gotta go back there. For some reason, I skipped C4. I didn't have it written down here. So remind ourselves to do C4. So that 1 is for C2. We'll check C4 here. It's gonna end up being -1, but we'll get that in a second. And then right now we're in the middle of doing C2 prime. So C2 prime, x went to x, and y goes to -y. So xy, because it's spinning y to -y, you have a vector there, it's going to go to the negative self, goes to x times -y, which equals -xy. So x is going to -xy, which is equal to -1. C4, let's go with that. X goes to y, remember on this one, and y goes to y goes to -x. And so xy goes to y times -x, which is equal to -xy. So we got a -1 there. C2 double prime. C2 double prime, we have x and y going into one another. So x went into y. Remember, C2 double prime is a rotation that way, 180 degrees. So it's a little hard to visualize, but it's an off-axis rotation, which causes them to go into one another. X goes into y, y goes into x. So xy goes into yx, which of course is just equal to xy. So xy went to xy, which is equal to 1. Inversion, definition we start with, x, y, z. Goes to any point, goes to -x, -y, and -z. And so x goes to -x, y goes to -y. And so xy goes to -x times -xy, which is equal to xy. So xy went to xy. So for inversion, we get 1. S4 is, by definition, a C4 followed by a sigma H. We know sigma H doesn't do anything. We just talked about this because it's in the XY plane. So it's the same thing, going to be the same thing as a C4. And a C4, we got a value of -1. And we just said sigma H doesn't do anything, so that makes it a +1. For sigma V, we had a mirror plane in the XZ. That was one of our sigma Z's. And so the x vector, because it's in the xz plane, is not going to do anything. So this is sigma v we're talking about now. X goes to x, but a y vector is going to be to the right of this mirror plane. So it's seeing itself in the left of the mirror plane. So xy goes to x times negative y, which equals a negative xy. So it goes to the negative of itself, -1. And then sigma d, x and y, sigma d is on this off axis. And so x and y look at each other, they interconvert. And so it's the same situation as the C2 double prime, where they interconvert, and you're going to get this same math here, xy going to yx, which is equal to xy, which is equal to going to itself, which is equal to 1. So there's xy. Same exact business now we can do for x squared minus y squared. That's the other one of these. So here again, we go to identity. Well, x goes to x, y goes to y. So x squared minus y squared goes to, well, x squared minus y squared. So that's going to be 1. But we could do it here for the C2, x1 to negative x. So let's see, x squared minus y squared goes to quantity negative x squared minus y1 to negative y, quantity negative y squared. That's equal to x squared minus y squared. So for C2, actually, we got a value of, this is C2, we got a value of 1. Okay. For C4, we do C4 up here. X squared minus y squared. Well, x1 to y, so that's a y squared. And y1 to negative x, so that's minus quantity minus x. We're subbing in y for negative x for y, right? And so that equals y squared minus x squared, which is equal to negative of the quantity x squared minus y squared, which is what we started with. So we got to the negative of itself. So we're going to have a -1 for C4. For C2 prime, we had x going to x. So x squared minus y squared goes to x squared minus, and y went to minus y, so minus y quantity squared. And so that equals x squared minus y squared. And so x squared minus y squared went to x squared minus y squared. So it went to itself. And so we're going to get a 1 here. And then for C2 double prime, x went to y went to x. So that's going to mean for x squared minus y squared, that's going to be y squared minus x squared. As we figured out last time, y squared minus x squared equals the negative of itself, of what we started with, negative quantity x squared minus y squared. So it's going to be -1. Inversion, well, x went to negative x, y went to negative y. So x squared minus y squared equals, or goes to negative x squared, quantity negative x squared minus quantity negative y squared, and that equals x squared minus y squared. So we get a value of 1. S4 was C4 followed by sigma h. Well, we know the sigma h isn't going to do anything because x goes to x and y goes to y. So really it's a question of what does the C4 did, and the C4 gave us a -1. So again, we have a -1 here. And again, we have a 1 here for sigma h because we said it doesn't do anything, x goes to x, y goes to y. Sigma v we did down here, x went to x and y went to minus y. So x squared minus y squared goes to x squared minus a quantity minus y squared, which is just equal to x squared minus y squared, which is equal to 1. And then our last one is sigma d, that interconverted the two. I didn't have that one written down, but that's x minus y, and x goes to y, and y goes to x. And so x squared minus y squared goes to y squared minus x squared, which, as we've seen before, is equal to the negative of what we started with. So we put down a -1. And so at this point, we have done all the quadratics. We thought about all the quadratics. Z squared didn't help us, equals to gamma 1. But we're almost home free. We just have 3 more irreducible representations to do. And so what we're going to do in the next video, part 4, is finish this up and uh, use some cubic functions to help us derive the remaining irreducible representations. And then we'll be able to do the Mulliken symbols on the left side and actually give those proper labels.